Hello and welcome once again for another ES340 example problem video. This is day 14 example problem 1. So we start off with a rigid insulated container fitted with a paddle wheel which contains 4 pounds of water, initially at 220 degrees Fahrenheit and a quality of 50%. The water is stirred until the temperature is 350 degrees Fahrenheit. For the water, determine the work in BTU and the amount of entropy produced in BTU per degree R. Okay, so what we have here, I think this is per pound actually, times degree R. Well, we can, no, we have the mass, so I'll leave it that way. So for part A, basically, we're going to want to, of course, immediately we should be thinking the energy balance equation. And for many of these problems, like finding a property, is going to require us to use the energy balance equation. So if you don't know how to find one of the properties, the first thing you should go to in your head is, oh, I need to go to the energy balance equation, okay, and I need to do that. Now in this case, it's not the energy rate balance equation because we have a closed system, right? We have a rigid insulated container. So since we have a closed system, we don't need to we can just use the energy balance equation rather than the energy rate balance equation, which we used so much before. And basically that just tells us that delta E is equal to Q minus W, which is also equal to delta U plus delta KE plus delta PE. Okay, and in this case we have no information about the velocity or change in height, so these terms are going to go away. And because those terms, again, remember, we always have to figure out which terms we can eliminate, and in this case we can eliminate those ones. In this case that means that we're going to have Q minus W is equal to delta U. Okay, and furthermore, if we examine this problem a little bit more, I just realized we can also eliminate Q, right? There's no external source of heat transfer. So essentially, we're going to get minus W is equal to delta U. Or if we want, W is equal to minus delta U. And I'll just write it out as in terms of U, capital U. Capital U2 minus capital, this is going to be, if I distribute the negative sign, it's going to be U1 minus U2. Minus delta U is U1 minus U2. Obviously, plain delta U would be U2 minus U1. Just keep that in mind. And then finally, because we're going to be dealing with tables, this is going to be equal to the lowercase u1 minus u2. Okay, good. So that's our energy balance equation and our entropy balance equation, because we're also going to need that for part B. Well, that's going to be delta S is equal to, again, we have this from state 1 to 2, the integral of delta Q over T plus sigma, but there's no heat transfer in this problem, so that goes to 0. So that means that our delta S, capital S here, is equal to sigma. Okay, so we'll be able to find sigma, which is the entropy produced. That's going to be sigma, by finding the change in entropy here. Okay, so now let's get into the nitty-gritty. We're going to need tables. I'm not going to show the tables at this point. I hope everybody can if you need to go back to the prior videos, and look at how to look at things on the tables and whatnot, please do so. But I'm going to assume that you can do that at this point. So from table A-2E, notice that we have a quality of 50% and a temperature of 220 degrees Fahrenheit, so we can find that value on the table. And all that we have to do is then find well, because it's a mixture, we're gonna have to find we're gonna have to find where the specific volume and things are in the mixture at 50% quality. So we know X is equal to 0.5, VF is equal to 0.01677 feet cubed per pound. That's just coming off of the table here. VG is equal to 23.15, again, feet cubed per pound. UF, that's the internal energy, because we're going to need the internal energy, right, to find the work here. UF is equal to 188.2 BTUs per pound. And UG is equal to 1079.8 BTU per pound. And SF, because we're going to need the entropy, obviously. This will be M times S2, lowercase s2 minus s1 equal to sigma, just as a side note here. So we need these lowercase s's as well. SF is going to be equal to 0.3241 BTU per pound degree R. SG is going to be equal to 1.7441 BTU per pound degree R. And we can just use the equations, right? So V1 is going to be equal to VF plus X times VG minus VF. And if I substitute these values into this equation, I find out V1 is equal to 11.5834 feet cubed per pound. Remember, this equation is used whenever we have a quality, or if we have to find a quality. You can also use this equation, rearrange it. Let's see, we have U1 is equal to, again, UF plus X times UG minus UF. So U1 then is equal to 634 BTUs per pound. And it's the same equation here, so I'm not going to bother writing it out again. It's the same idea, just replaced with S. Now is equal to 1.0341 BTU per pound degree R. And that just is that's at temperature 220. I probably should have written that down. T1 equal to 220 degrees Fahrenheit. So all of these values came from the 220 degrees Fahrenheit there. Now at state 2, what do we know? Well, the first thing is this is a rigid container. So rigid means that the volume does not change. So that means V1, this is why I needed V to begin with. Excuse me, V1 is equal to V2. And that was, we found it up here, V1, 11.5834 feet cubed per pound. We know that T2 is equal to 350 degrees Fahrenheit. And by the way, the reason that we know that we have work, right, I forgot to probably mention that, is that it's stirred with a paddle wheel, right? So we have some external thing that's providing work, or perhaps extracting work, depending on the scenario. The fact that it's being stirred probably indicates that it's work being done by the paddle wheel, so on the system. So we have T2 equal to 350 degrees Fahrenheit, and we know what V2 must be. What we find is at this temperature, and specific volume, this is superheated, right? So the specific volume is larger in this case than the vapor, the specific volume of vapor at that temperature. So because it's larger, since V2 is greater than V saturated at 350 degrees Fahrenheit. So we use table A-4E, and at that temperature we need to interpolate that temperature and specific volume. And I think I've done enough examples of interpolation as well, so I'm going to assume that you can do the interpolation here. But what we find is U2 is equal to 1,124.02 BTU per pound, and S2 is equal to approximately 1.7281 BTU per pound degree R. Therefore, we can actually now find the work, right? Because we have this equation here. So the work is going to be equal to the mass, which was 4 pounds, times U1 in this case, right? That negative sign got carried through. U1, which was up here. Where did I write it down? Here we go, 634 BTU per pound. Minus U2, which is 1124.02 BTU per pound. And what that comes out to be is minus 1960.1 BTU. So that's my amount of work done. And then up here we also found that this was the case for sigma. So that was this was part A. This was the answer for part A. And then for part B, using this equation that we found earlier, right, there was no heat transfer, so we didn't need to involve the heat transfer in order to find sigma. Sigma must then be equal to 4 pounds times 1.7281 BTU per pound degree R minus 1.0341 BTU per pound degree R, which is equal to 2.776 BTU per pound, BTU per degree R, since we multiplied through by the pounds there. Okay, that's all that I have for this video. Hope to see you again soon.